Let's look at the third graph. This one's very similar to the one that we did on the other side. But if you notice that this here has an open circle. So let's just go ahead. I'm going to highlight some things. This one's actually a little easier to talk about, I think, in some respects. But we have to be careful here. So remember, our domain, that's our x values. So all values of x, which means I'm going to hold my ruler so that it's always touching my x-axis. So it looks like this function begins right about here at x is 1. The problem is I have an open circle, so it cannot include 1. So I'm going to use this symbol to mean not include 1. It's going to get really close. And now it touches the function all the way up to here where x is 1, 2, 3, where x is 3. Because this is a closed circle, I'm going to put a closed bracket. So set builder notation would be the set of x such that, well, where do I start? I start at 1. 1 is less than 3, right? So I'm going to write my 1 on that side and my 3 on that side and my x in the center. But it doesn't include 1, so there's no equal sign. It includes 3, so I have to have less than or equal to there. So let's look at for range. So for range, I'm looking for my y values. So with y values, I want my ruler to always touch my reference, which is my y-axis. Start from the bottom, and my function begins about there. So that's where y is 0. So it doesn't include it. So I'm going to have not including, but starting at really close to 0, and then I go all the way up to here. It stops. There's no more function after that. And that's where y is 1, 2, 3, 4, 5. That's where y is 5. And it includes 5 because I have a closed circle. So this would be the set of y such that I start at 0, but not including, and I go all the way to 5, and I include 5. So I just want to let you know, these are not points. Those are intervals. That's the value between here and here is the interval for x, and the value between here and here is the interval for y. So let's talk about zeros. So this is an extremely important vocabulary word. This vocabulary word will come up again and again and again. So again, let's just put this down. So if I'm talking about zeros, that's the same as x-intercept. That's where I'm looking for the value of x when y is 0. This is an actual point. So let's look here. This is where y is 0. Y is 0 where? On my x-axis. Let's write that down. So y, the line y equals 0 is the x-axis. In Algebra 2, the x-axis is everything. It's where we find a lot of our solutions for our functions. So right here is where the 0 is. So do I have y equals 0? No, I don't. So this does not exist. There is none. And again, we could go ahead and talk about the increasing interval, decreasing interval, constant interval, and behavior. But this is the key thing that I wanted to show you on this graph, and I would like for you to try to figure out the rest on your own. Okay, so let's look at number 5. So clearly, let's ask ourselves, first of all, let's make this simple. Is this a function? So if we do the vertical line test, that means that I'm going to, if I were to draw vertical lines, it can only touch the ruler in one place. But we can see I'm touching the ruler here and here, here and here, here and here. So this here actually fails that vertical line test because I have more than one place where that ruler, that vertical line is touching. So this here is not a function. So if something is not a function, we do not talk about functions, which means that we can not do any of that. The only thing that we would maybe want to look at would be the zeros, but even then, I mean, there might be a zero right here if that were touching. It doesn't look like it is. So we can actually not do any of this. The fact that this is not a function, we can't talk about function behaviors. However, we can still talk about domain and range. So I'm going to let you try to figure that one out on your own. Let's look at number 15. Okay, so let's talk about domain and range. Well, first of all, clearly this is a function. Why is it a function? Because if I were to do the vertical line test, it only touches at one point on that vertical line. So this is a function. It's a kind of a skinny function, but this is where students get a little confused. So remember that domain, again, those are our x values. So when we're talking about x values, my ruler always touches the x-axis. So it's very easy for people to think that my function begins right here on the left. It does not. So what I want you to do is I want you to imagine, and I'm just going to use this little piece of paper here, I want you to imagine that this function doesn't just stop there. It eventually goes further and further and further and further out to the side. As I go down, it's going further and further out, as you can see from that little piece of paper there. It's going further and further and further out, which means that this is infinitely wide this way, and same thing here. As it's going up, it's getting wider and wider, which means that it's going to be all values of x. So my interval notation is going to be from where x is negative infinity to where x is infinity. So for set builder notation, we would say the set of x such that x is the set of all real numbers. Okay, so I'm just going to write this right here, that this means all real numbers. Okay, so now when we're talking about range, again, ranges are y values. So when I'm looking for y values, I have to make sure that my ruler is always touching the y-axis. This one's a little easier to see. This doesn't start here. See that arrow? That means it's starting way down here. And it goes up and up and up and up and up and up and up forever. So this here, actually the domain and the range on this function happens to be the same. So we would say the set of y such that y is the set of all real numbers, and again, all real numbers. So for this function, you might recognize it as a cubic function. So let's just write that down here. Cubic function. Okay. And a cubic function, I don't know if you remember, but a cubic function, the parent would be y equals x cubed. This is not the equation of that. It's just the family that it comes from. So that's the family of cubic functions. And when we talked about that earlier, we said that for cubic functions, the domain and range are always that. So let's talk about zeros. Again, zeros. Let's write this down. Zeros. That means our x-intercept. That's where our function equals 0, or our value of y equals 0. The other word we can use is root, and we can use solution of the function. And sometimes we're lazy and we just say solution, but we have to look at the rest because there's also a solution of a system, which is totally different. So let's talk about our x-intercept, which is right here. So again, we're going to have to approximate what that 0 is. So that looks like that might be negative 4.6. Okay? So we're just going to estimate that at negative 4.6, and that's where y is 0. Again, remember that this here is a point, and that's our x-intercept. Our x-intercept is where we have a value of x, and y is 0. So increasing intervals, how can I tell if it's increasing? So what I want you to do is I want you to think slope. So I'm just going to write this down. Think slope. It's not technically a slope, but let's think about slope. If I take my ruler and I go from end to end of that function, from here to here, that's always a positive slope. Even here, there's really not, it doesn't look like it's kind of like levels off here, okay? So this means it's always increasing, so there is no decreasing, none. But again, remember, increasing interval is where my function is going up and up and up. So it looks like it's going up from where x, the value of x, not y, the value of x is negative infinity, and it draws it all the way up to where x is infinity. Okay? This is where it gets a little confusing. You could argue that maybe this is flat here and that this is constant, but I'm going to tell you that it's not. So for constant interval, I'm going to say none. So let's look at end behavior. So when we look here, this means as x is going to negative infinity. Well, where does x go to negative infinity? That's to the left. So on the left side. So what's happening on the left side? On the left side, my function is going down. So my function is going down. So that means my function is going to negative infinity. This means as x is going to infinity, well, x is going to infinity would be the right side. Which way is my function going? My function is going up. So that means my function is going to infinity. The only time you're going to look at arrows is when we look at end behavior. So let's just write that little note. Only time we look at the arrows, because that tells us the direction that the function is going.